The integrals and derivatives of calculus allow us to draw conclusions about a function based on information about its derivative and its second derivative. This is used extensively to solve optimization problems, like what's the maximum profit a company can make, what's the maximum distance the Bay Bridge will sway during an earthquake or a windstorm, that kind of thing. This sort of analysis is super important because this is the sort of thing that happens when a bridge moves beyond its calculated maximum. This is our very own Bay Bridge in 2009. Basically, a windstorm made the bridge sway a whole bunch. It went too far beyond its calculated maximum, and a reinforcing metal chunk fell on the bridge during rush hour. Oops. Fortunately, no one was injured, but had that truck there been a little bit closer, it would have come down right on top of the person inside. Phew, very, very close call. So this stuff is really important. It's a lot of what calculus is used for in the applications. And our goal for today is to figure out how a function, its derivative, and its second derivative are related so that we can use one to figure out information about another. So for example, we can use a derivative to figure out when a function has a positive or has a maximum or a minimum value. So to do this, we're first going to look at a function derivative and second derivative that occur very nice and analyzably in nature. That's position, velocity, and acceleration. Remember, change in position over time, that's velocity, that's its derivative. Change in velocity over time, that's acceleration, that's the derivative of that, or the second derivative of the original function. We'll observe the relationship between the graphs of these as Moving Man moves, and then we'll talk about what these mean for f, f prime, and f double prime in general. Remember what these graphs are showing. They're just tracking, graphing Moving Man's position for this top blue one. As he moves, his velocity, more and more and more positive, less and less and less positive until it's 0. Right there, and then going back in the negative direction, negative velocity there, and then acceleration. Which direction is his velocity changing in? Looking at a printout of these graphs, we can use them to try to fill in this table down here. What happens with velocity when acceleration is positive? How about position when acceleration is positive? What happens with acceleration when velocity is 0? And so on and so forth. So, let's look at these and see what we can find out. Let's first just look at when acceleration is positive versus negative. So there's a switch right here, and right here. And notice that when acceleration is positive, right here and right here, velocity is increasing both times. In fact, that's the only time that velocity is increasing. So what that means for us, it means that if acceleration is positive, velocity is increasing. And notice also, position is concave up here, position is concave up right here. Those are the only times when position is concave up. Looking at when acceleration is negative, notice velocity is decreasing both times. And position is concave down both times. When the acceleration is 0, so right at these points, velocity has either a minimum or a maximum. And by definition, position is switching from concave up to concave down, and so on and so forth. So position has an inflection point. Okay, so let's switch to looking at what happens when velocity is positive. So that's this next column right here. So here are the zeros. Velocity is positive, velocity is negative, velocity is positive, velocity is negative, velocity is positive again. There we go. So going up, we can see that when velocity is positive, position is increasing. Those are the only times when position is increasing. And logically enough, when velocity is negative, position is decreasing. And this makes a lot of sense because if velocity is positive, then the change in position is positive. Moving man should be going to the right. His position should be getting more positive. And notice when velocity is 0, relative maximum, relative minimum, relative maximum, relative minimum. Right there. Now let's look at what happens going down though. So positive velocity, negative acceleration, negative velocity, negative acceleration, positive acceleration. There doesn't look like there's any relationship here. When velocity changes from positive to negative, that's not telling us anything about acceleration. Okay, so let's go ahead and look then at our final row. When position is positive versus negative versus 0, what does that mean? Well, position is negative all the way up to 10, and then positive the rest of the way. So if we look on this half of the graph, velocity is positive and negative, acceleration is positive and negative. And same thing for when position is positive. So it turns out that position being positive, negative, or 0 actually tells us absolutely nothing about this left side of the graph. So positive, negatives, and zeros are filling in the right side over here. And notice there's a pattern. Positive to increasing, positive to increasing. Increasing to concave up, well that's the only concave up, concave down we have, so we can't tell if there's going to be more of a relationship here. Now, let's add in a little bit more detail about these relative maxima and minima. Notice that for velocity, velocity has a relative minimum when acceleration changes from negative to positive, and velocity has a relative maximum when acceleration changes from positive to negative. So let's just write this down here. A maximum for velocity occurs when acceleration changes from positive to negative. And that also holds true for velocity to position. A maximum for position occurs when velocity changes from positive to negative. And similarly, a minimum for velocity occurs when acceleration changes from negative to positive. Same thing for position, which has a minimum when velocity changes from negative to positive. and then also an inflection point for position occurs when acceleration changes sign. So that's positives and negatives. Or velocity has a minimum or maximum. Now, we know that these are holding true in this one graph that we saw, but let's just check another couple examples to make sure they're always going to hold true. Now, let's look particularly when velocity is 0. That's what we're looking at right here. Here we said position has a relative minimum or maximum. However, right here, velocity is 0, but position flattens out, but it doesn't have a minimum or maximum. It flattens out a little bit and then keeps going down. So one of the key things to note here is that when velocity is 0, position may have a relative maximum or minimum, but it doesn't have to. Really, it's only if velocity changes sign. Notice that velocity is negative, then velocity is negative again. That's why we don't have a maximum or minimum here. At this 0, velocity changes from negative to positive. Lo and behold, there's a relative minimum. This also holds true if this is acceleration. Then we'd be talking about velocity, acceleration. So that 0 on that other page really ought to be changed just a little bit. We really ought to be saying for these relative maximum and minimum, may have. Down here, may have. And if we have a may have for this one, let's check this one and see if it's really true that there has to be an IP, an inflection point. Well, notice over here that acceleration is 0, but this is a flat line, or a straight line, excuse me. There is no inflection point here, so we can say the same thing when acceleration is 0, position may have an inflection point. However, only if acceleration changes sign. So coming back to here, same thing, we should really update this. May have. So now that we've looked at these relationships in the real world, it's really important to memorize a generalized table for the relationship between functions and their derivatives. And what this really is it's really a translation dictionary to translate from F to F prime and so on, just like we would translate English to Spanish or any other language. So this is just going to be a shorter version of the original table that we figured out. This is f double prime, f prime, and f. And remember, this corresponds to acceleration, velocity, and position. And now we're just going to record the relationships that we saw. We saw positive negative 0 translates into increasing decreasing and extrema. Maybe. Translates into concave up, concave down, and inflection points. Again, maybe. Now, we just move over positive negative 0, increasing decreasing extrema. Maybe. And then the final moves over one level. Positive negative 0, positive negative 0, positive negative 0, extrema, extrema, increasing, decreasing, and then the concavity in the corner. This is incredibly important. This must be memorized or the dragon will come and gnaw on you. Very, 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 very important. I actually made myself a little card with it on it, just so that I would have it to refer back to as I was memorizing it. A couple of things to note. Leave yourself some room over here. We're going to add something else in here. But minima occur if the function to the left changes negative to positive. Maxima occur if the function to the left changes positive to negative. IP occurs if the function 2 to the left changes sign. Over here, I'm going to give you the expanded table. Notice that there are patterns over here, where basically just these diagonals are the same. So one of the things that we could do is we could actually just expand this table both up and to the side. So here I'm going to do f double prime. Here I'm going to do f prime. Here I'm going to do f. And here I'm going to do the integral of f. We can start with what we have over here. You should be able to fill this in quite quickly. Positive negative 0, positive negative 0, positive negative 0, inc dec ext, inc dec ext. But notice that we don't have to stop there. These diagonal patterns just continue. So what this means is it means that if we're asking about the integral or the antiderivative of f, and we know that f is an increasing function, then the antiderivative is going to be concave up. Just like we can translate with these three right here, if acceleration is positive, we know that that position is concave up. If f double prime is 0, then we know that there's a possible extremum at f prime, and so on and so forth. We can also expand that even further. What you should have memorized is you should have this table over here memorized, and then you should recognize the pattern so you can expand it into this table if and when you need to.